Good morning, I'm Technical Sergeant McCusker. This is Block 2, Unit 3 Alpha, Class 20034. We're going to identify the relationships of basic facts and state general principles about the functions of the HF transceiver module. As always, the test requires a minimum of a 73 to pass, meaning you need an 11 out of 15, but we're going to do way better than that, correct, Aaron Rodriguez?
Yes, sir.
I like it. At least an 80. We got to shoot for that.
At least.
At least. You guys can do it. I believe in you. There are many HF radios in our career field. Typically, I will read this like I am the gunny pile guy reading this in Full Metal Jacket, but today is a little more chill today. So each may be slightly different, but the basics are the same. Understanding the following theory and block diagrams will give you a better understanding of how these HF radios function. Aaron Sotelo, why do you think we might want to do this?
What do you mean exactly, sir?
Why should we understand how the guts of a radio work, basically? What will that help us do? I mean, we know we talk about swaptronics all the time in maintenance and how we're not really maintenance in this career field anymore. But for you, what would understanding the guts of a radio help you do?
Well, it would help you to better understand when a problem arises, exactly which part might be responsible, aid in troubleshooting.
Wow, that is outstanding, and the first class I have ever heard give me the exact answer I wanted to hear. I applaud that.
A plus, good job still.
That was A plus. I would have pulled a digital 341 if it were possible for excellence right there. Yeah, that is exactly what I wanted to hear. So it'll give you a better understanding of how it works. And like you said, even though you're not going to be the one who's necessarily going to do the maintenance, by understanding those troubleshooting techniques and tactics, you can send this radio back to Harris with a much better know-how and notes on there saying, like, this is exactly what's wrong with the radio. We know what's wrong with it. Please look specifically at this section. Makes sense?
Yes, sir.
Yeah, remember that, guys. Even though things are under Swaptronics, it doesn't mean you can't do maintenance. Just know what radios you can open and which ones you can't.
Is there someone higher up that we'd have to ask before doing so, obviously, though? Like our
Yeah,
supervisor?
so for the Harris radios, and this is something Sergeant Gass and I typically preach to y'all on day 4, which would be tomorrow for y'all, is if you have an opportunity in your career to go to what's known as the Level 2 Harris certification course, I 100% recommend you fight tooth and nail to get to that course because, one, it's very expensive. Two, it's a certification that not a lot of people have. It's like a lifetime certification from my understanding, too. It doesn't expire. So it's not like Net Plus or Security Plus where you gotta take something new every 3 years just to renew that stuff. And it'll also help you on the outside because not a lot of people have that certification.
Cool.
Yeah, it's pretty neat. I missed out on an opportunity at my last base, but I was in quality assurance, so they weren't going to send me. So we have these things called assemblies. That's one of the things we're going to talk about today. The hub battery, which does what? We talked about this yesterday. Airman Smith, what does the hub battery do? Make sure you push that push to talk. No, it does not do silence. Is she typing? All right, somebody else. Airman, right. What does it do? The hub battery.
Is that what gives it the power in the first place?
Not the power for the radio.
The hub battery keeps the memory.
Yeah, it keeps the memory of the radio, exactly what she's saying. It maintains the control and system status functions for the radio when the radio is off. It's that 2.6 to 3.6 volts. I can never remember the exact number, which luckily I don't have to because that information's in your what?
TO.
It's in your TO. It's in your commercial operations manual, so you don't need to remember the voltage. You just need to know what it's capable of doing. And that's what Sergeant Gaston was talking to you guys about on day 1 is we don't need to necessarily know specifics of things. We just need to know what they can do a little bit, like a broad strokes general kind of overview, like you're Bob Ross there and you're painting some happy trees, some happy clouds. Just a broad strokes overview there. So we got this transmit signal flow thing. That's one of the first things we're going to talk about. That's how the signal is traveling through the radio as you, the human, speak into the radio or type, which is data. Are two types of intelligence, correct? Audio and data.
Yes, sir.
Awesome. So then we have clear voice, which is what? What was clear when I said yesterday? You guys remember? What mode? What function?
Plain text.
Plain text mode is clear voice. Very good. What does that mean?
There's no encryption on there.
There's no encryption. It's a lot easier when you can see the word encryption right in front of your face, isn't it?
That sounds about right. Yeah.
Yeah. Okay, that's honest. So data is where J3 is. That's where our data is going to come in. And then if we transmit something, it has to do what? We're not just shooting signals off into space, are we? We're hoping that it goes where?
To a receiving antenna.
Yeah, to a receiving antenna, to a distant end. That's where our receive signal flow comes in. And then we're going to talk about that, which will be a lot easier because you guys will already understand how the transmit signal flow works. And with this radio, a lot of the things that happen in transmit also happen in receive. We're going to talk about the theory of operations first. That's our first category here. I'm going to give you guys different clarification for assemblies and sub-assemblies. They are two different things. You may hear that as module and sub-module. Those are interchangeable words for assembly, sub-assembly. I know what it says under here, but I'm going to just show you guys because it's way easier to do that than sit here and read. When we talk about an assembly, we talk about this guy right here. Enhance, enhance, enhance. There you go. We talk about the A2 lower chassis assembly. What do you guys think that encompasses? If you guessed everything that I just highlighted, you're correct. When we talk about the A2 lower chassis assembly, that is a module or an assembly. It encompasses everything that's happening inside of this area here. Now, if I wanted to get more specific, I would go to A2, A4 and ask you what's happening in here, such as cleaning up the audio, changing it from analog to digital, routing our traffic as it goes through, things like that. When we talk about our sub-assemblies, we're talking about specifically what is happening inside of that sub-module there. Make sense?
This putting inside the radio itself as we're putting a signal into it.
Yeah, it's like radioception. I want to know inside of a module,
Awesome.
inside of a module, what's happening. Now, we all passed kindergarten, hopefully. So when we look at these dotted lines here, just like when you're cutting out on a piece of paper for the first time, you're going to go make that homemade project for your parents. You cut this line out. If it is not inside of this line, it is not a part of this subassembly. Does that make sense?
Yes, sir.
I say
Yes,
that because what happens right here? What do you guys notice?
That looks like something that you would add when you're trying to add encryption to the
Yeah, that's
signal.
for CT mode. Yeah, it's specifically going to go to the A2, A5 if we're going to do CT mode for our function switch. Very good. All right, we'll come back to this. Awesome. You guys are going to crush it today. I like this interaction. It's usually like pulling teeth on this section, but this is great. So I'll just read this little verbiage down here for y'all. A2 is a designator for the entire assembly. Like I said, this assembly has many submodules. For example, A2A1, A2A4, and A2A5. That's just a few of the ones I just showed you. These submodules each have a separate job or function in the radio. But when I ask you what A2 does, I don't want to know that. I just want to know what is A2 doing in general. And you may see questions like this on your exam, so this is very good to pay attention to this stuff, guys. Does everybody have their intermediate maintenance manual pulled up? Table 3-1. Okay,
No,
so
sir.
go
I
ahead, take a
can't have
second
both
and
at the same time.
okay. So make sure you're going and looking at it afterwards then, and I would write these references down because what I'm
Yes,
going
sir.
to go through right now is literally going to transfer to your TO. And maybe if you're listening to this recording afterwards, you can just go through and follow along with that. So we talk about these assemblies, these things I was just talking about. We go through A1, A2, A3, A4, A5. And these are all the kind of things that you probably should only really recognize this one. That's the only thing you guys have touched before. The KDU. That's your key display unit where you guys are programming the radio on. This is what it looks like if we were to like blow out the radio, for example. Here's our A3 right here. So if you were to take this apart and you were in a secure environment and following all those great CCI rules that you had to do, this is what it would look like on the inside of the radio. Here's your A2 here. This is your A1, A4, and here's your A5. The first thing we talk about is A1, and I like to compare this to a turtle shell for two reasons. One, the radio is green, and two, a turtle shell does what, Airman Rodriguez?
Protects the turtle.
It protects the turtle. What do you think our A1 chassis is doing for the rest of the radio?
Protects the radio.
It's protecting the radio. It's protecting those guts of the radio, just like the turtle shell is meant to protect the guts of the turtle. A1 protects the A2 lower chassis assembly and the A3 upper chassis assembly. It receives direct current power from A4 rear panel assembly and distributes that DC power to the other receiver transmitter assemblies. It provides a mounting structure for the front panel interface connectors and the KDU. This KDU actually detaches. That's what they're talking about for a mounting structure right there. That's what they mean. I'm sure you guys didn't do that in class though.
No, we did not.
Which is probably a good thing, because if you ever have to do maintenance on these, don't remove the KDUs. Just don't. Or if you do remove it, to blow the dust out of that little TA3 connector, rose connector in the back there, make sure you put it back on immediately, because the KDUs are what's known as MAC addressed to that specific radio, which means it's the physical address. You can't swap them. They're not interchangeable.
Why is that so?
I'm assuming it's a security feature. If you have to, let's say, for example, just go somewhere real quick and you can't bring the radio with you, or you're in it, a situation, and the radio is just, it's either something happened to it or whatever. You don't want the enemy to be able to take that radio and use its crypto, or maybe something that might have been in there. Maybe you didn't have the time to zeroize it. Who knows? But by separating these two things, you make that impossible. Yeah, there's a whole list of like things I could honestly go through with you, but it really comes down to security. So A2 processes the voice and data signals. It supervises control functions for the entire radio. It also contains the encryption crypto assembly. And then we go to A3. And remember, this is those broad strokes, general terms I was talking about. We're going to get way more specific in a minute here. And yes, I do keep saying Pacific. A3 contains the analog RF sections of the radio. It has the receiver, the exciter, the filters, the power amp, tuning circuits, and an analog output of 240 kilohertz, known as the first IF, which is going to be important. A4 is our rear panel assembly. It contains the radio power supply. This is where you guys plugged in the radio the other day when you were putting those battery packs on. Do you guys remember doing that? Yeah, did anybody turn it upside down?
No, sir.
By mistake? You can actually do that. You can take the battery pack and turn it the other way around because of the way the connectors are positioned. You can do that. Now, don't turn the radio upside down itself and try to figure it out. You're going to have a hard time. Okay. But you can do that. It provides the interface connector to the batteries and also has that hub, which Airman Smith said does what? What's the purpose of the hub?
It saves the information.
Yeah, it saves your information. Can we save that information if we zeroize the radio, though?
No.
No, because it wipes it completely.
Yeah, no, it'll wipe it completely. You gotta start from scratch. Very good. I think you guys got to do that as well the other day. So you probably saw that firsthand, what happens when you zeroize it.
We did it initially just in case, then we did it afterwards as well.
Yep, that's good. It's always good to zeroize your radio when you're done with it, especially on exercises. You don't know if you're going to have those same frequencies authorized to you again next time, so you don't want to just get in the habit of using the exact same frequencies every time. So the hub is the hold-up battery, like you guys said. It's for protecting the memory. That's that system status stuff. It's important to the radio because if you have to go somewhere, let's say you're programming a bunch of radios and you don't have that CPA, that communications planning application, you might want to save your progress basically before you go to lunch or things like that. It's just like PS2 with a memory card. If you don't have your memory card in, you can't save your progress. So J9 accessories, that's the one that we're going to do what with?
Not touch.
Not touch. Very good, Aaron. Right. Now I'm questioning whether or not you touched it just to be like, haha.
I said when we first got to the lab, I said, Sergeant Musker actually said these are the ones that we go to for.
What did you call me?
Is it
Musker? That's a new one.
McCusker.
That's definitely how you
But
say it, but I like Musker. That's a new one.
the other, as soon as we got to the lab, I told
Sergeant Gaston.
Sergeant Gaston that was the one that you told us to touch first.
Nice. I'm sure he laughed.
He did.
Yeah, great. J10 and J11, that's our battery connectors. That's funny. You guys are going to get me fired. Alright. So your battery here, this is your hub. This is about how big it is, too. I mean, it's a small green and white battery. It's only a couple volts. And like I said, it's not meant to power the entire radio. That's not its purpose. That was just a diagram where the hub goes. A5 is our KDU. A5 contains the keypad and the LCD that makes up what's known as the MMI, the man-machine interface. You may hear this possibly on your exam. There's another name for the A5, and the other name is the A5 KDU or the man-machine interface, MMI. They're interchangeable. So they may ask you, like, what is A5 doing in the radio, or what is the MMI's purpose, or something like that. It's been a minute since I've taken this, so I don't know exactly. The intermediate maintenance manual, it's the transmit clear voice signal flow. That's what we're going to talk about next. I know you said you couldn't pull it up, Aaron, right?
Yeah.
Okay. Well, I highly recommend
I could
when
probably
we're
pull it
done
up.
here.
I just can't.
Yeah, I highly recommend when we're done here that once I get the video uploaded, maybe later this evening or even over the weekend, you watch the video and follow along in this paragraph, because what do you guys get on test day? I had a Freudian slip there and said the answer. Yeah. Yeah, your TOs. You get all your TOs. And you get this diagram.
Perfect.
Yeah. So when we come in the radio, one of the first things we're going to talk about is our transmit voice signal flow here. It's going to be clear, which means it's going to be unencrypted. So we will assume what mode are we in probably on the radio.
Plain text.
Plain text. Ooh, Rodriguez has got it. He's like, I'm just going to yell stuff today. I like it.
He got tired of hearing me talk is what it is.
Did he? Is that your Rodriguez?
Exactly.
Oh, I like it. Feel free to speak up. I like it.
Hashtag can relate.
Okay. When we come in the radio, do we come in as analog or do we come in as digital with audio?
Analog?
Analog, correct. Because that's what audio is, and nobody in here is a robot, are they? At least that I'm aware of. I haven't seen y'all in person, but I assume no one's a robot. So we got ALC, that's our first thing we're going to come in through. This J1, that's just the audio connector y'all were probably having trouble connecting yesterday, unless he left them connected for you.
He said we got all the easy ones, so we got to connect them. I guess there's some that work better than others, and
the O-ring is busted on some of them, and it doesn't connect as well as it should. Or the newer O-rings, when I replace them, they don't work very well when you first put them in. They are very resistant to getting on there. It's a pain in the butt. All right, so the ALC is the first thing we come to. That's called the automatic level control. It adjusts the varying voice levels entering the radio. So if you're talking really low, or if you're talking really high, or somebody has a squeaky voice or something like that, it's going to make those a normalized level, basically, so that it can go through to this next part and get digitized, and then kind of get cleaned up and sound more like your original voice. We don't want fluctuating voice levels coming through the signal, or the radio, especially these sensitive circuits, because you could end up damaging some of them if they're not at the levels they're supposed to be as they come through here.
I'm sorry, you said level? The adjusting level?
Yeah, so the signal level. So when you talk, it gets measured in dBs, right?
Yes, sir.
It's measured in hertz.
dB is decibels, which is hertz.
dB is decibels, yeah. But that's, well, hertz is a different thing. But yeah, dB is decibels. Yeah. So the dB refers to the signal level. Hertz refers to how fast the signal comes through, the frequency, right? Your CPS, your cycles per second.
Yes, sir.
Okay. I just wanted to clarify that for you. That's okay. AIC is the next thing we go to. That's okay. Your interruptions are perfectly fine. I don't mind. AIC is the next thing we go to. That's the analog interface chip, not the A1C. If anyone's looking at this on their own diagram, that's not A1C. It gets confused a lot. This is going to take that analog signal and digitize it. Why do you think we're going to digitize it?
That way we can have some type of data to send through.
Okay, some type of data to send through. That's not wrong. We do want it to be in data format, yes.
I'm thinking it's so that it can be received in different ways or different radios?
Okay. All of these are good answers, but not the one I'm looking for. All right. So the only reason really, and it's a real simple one, is because things are easier to manipulate when they're digital. That's it. It's just easier to modulate and manipulate a digital signal versus an analog one. And you'll see that when we come down to the A3 section. There's a whole bunch of stuff that goes into manipulating and moving around an analog signal versus a digital one. Now that we're digitized, we're going to go to something called the VDP next. That's our voice data processor. It's going to enhance that voice and clean it up a little bit better. It's going to make it sound like your original voice. Has anybody ever used a crappy headset before? Or even
Yes, sir.
starting Gaston's headset as
Sure.
an
Yes,
example,
sir.
I'm going to call him out since he's not in here. But the headset he has, he actually told me is a little busted with the USB on the side where it actually connects. So that's why he sounds like he's cutting in and out. But this would make his voice sound more like an original voice representation versus whatever he was doing the other day. Make sense so far? Everybody's tracking?
Yes, sir.
Cool. You guys are good. This is interactive. I like it. Next, we go to something called the PTFPGA, or as I like to call it, the traffic cop. Why do you think I'm calling it a traffic cop?
Can you say again? Traffic what? Cop?
Traffic cop.
Uh,
He's from Boston, all right? He's a traffic cop.
mm, uh, stops the flow and kind of reads it and checks for anything that's not supposed to be there.
Okay, that's not bad. Where is he going to send it? What does a traffic cop do? I mean, they can stop the flow, but eventually it has to go somewhere, correct?
Yes, sir.
So where are we going to go right now?
Looks like it's sending it out. So is it
Mm-hmm.
to the other radio or to the receiving end, wherever that may be?
Not the receiving end. This is only the first subassembly. We got a lot more to talk about.
Ah, okay. Well then,
What does that function switch do again? That thing you guys have on the radio that we talked about yesterday during controls and indicators?
function switch.
Yeah. Anybody else can step in.
Is that converting it to the plain text?
Yeah, we're going to convert it to plain text if we have it selected for plain text. What about if we have it on CC? Where's that red arrow going to go?
To the encryption
Yeah,
or the
to CC, right?
embedded crypto assembly.
No, not if it's CC.
Oh, that's CT.
That's
Citadel cover.
CT. Don't confuse those two. Which one is for NATO and allies?
PT.
Nope. I like the confidence there, right, but wrong.
Gotcha.
Anybody else? There's 4 other people in here that could help them out. Which mode is for NATO and allies? Either CC or CT. It's a 50-50 shot.
CC.
I would go with CC. Very good. CT would go up here, like he was saying, and go to the A2A5. It comes out of the A2A4 and goes into the A2A5, its own separate crypto assembly, because this is the one, remember, we don't share. And it has to be loaded with a separate fill device. They do both come back into the radio, though, and go back through A2A4 eventually. And we'll get into that. Now, since it is audio or digital audio at this point, we're going to go through the CFPGA. That's the Control Field Programmable Gate Array. No, you guys do not have to memorize all these names like I have memorized. I've just been teaching this for a minute, and that's why I have them memorized. These names are all available in your TO in section 3.3.1.1, where it talks about transmit signal flow. That's your intermediate maintenance manual for the 150. Now, the CFPGA, it's just going to pass along that information since it's not plain text data right now. Otherwise, it would go to the modem, which is a modulator demodulator. That's what modem stands for. I know I just blew some people's minds right there.
We actually learned in EP.
Yeah, not everybody remembers it by now, and they forget it, and they're like, whoa,
It's
that's what
kind of
modem stands for. They have like a Keanu Reeves moment, like, whoa.
funny.
Yeah. Then it goes to CDSP, which is the Control Data Signal Processor, not ODSP. Or ODST is what I like to call it because that's what it makes me think of.
ODST.
That's what it makes me
Yeah.
think of whenever I see that. That's the Control Data Signal Processor. Again, just going to push along that information. Not really going to do anything with it. Then we go to the DIF ASIC. That's the Digital Intermediate Frequency Application Specific Integrated Circuit. That is going to do something with the digital signal. It's going to take it and convert it to what's known as the first IF of 240 kilohertz, but it is still digital at this point, and we can't really do anything with that in our analog RF section of the radio, which is known as A3. That's why we have to send it to the digital intermediate frequency digital to analog converter, which is right next to it, and take that signal and make it analog. So that way we can actually process it through our analog RF section of the radio. Any questions on A2 so far, since we just covered all of it?
It's just,
I know this is a lot.
I understand. Yeah, I understand why you're the matter of
Yeah, this
trying to remember is going to
takes
be on
a
us,
while.
obviously.
Yeah, this takes a while typically to lecture this portion for y'all because it's just a lot of information to go through. And I don't want to rush it because I want to make sure you all understand it. So
As of right now, I don't really
no
have any
questions?
questions.
Okay.
No questions at the moment, sir.
Okay, if you guys are waiting until the end for your questions, that's fine too. I don't mind hanging out afterwards either. That's fine. So anything less than 1 megahertz will pass unchanged to the next stage. This is going to get rid of noise. What is noise again? This is talking about our low power filter here, our low pass filter, that LPF, that first bullet up here.
That'd be distortion in
Yeah,
either.
distortion. It's that unwanted spurious signals or noise. That's what distortion is, or noise is. It's unwanted spurious signals or responses. It's things you don't want in your signal, basically. EMI is an example. We used that yesterday, and y'all, I know Sarboudro was in here when we used that. It was pretty funny.
We seem to have a lot of that distortion when we were
Yeah.
the handsets yesterday.
Yeah, that happens. That's because your squelch gates are not set super high, but we don't really let you guys mess with those. So the 240 kilohertz signal is attenuated at 13 dB. Do you guys understand what attenuation is? Because I know
do not,
most
sir.
people do not when I start talking
Somewhat.
about this. Okay. Remember, dB is how we're measuring our signal level. Now, if we're not amplifying it, typically the other word is going to be attenuation. Attenuation is going to take the overall signal level and basically make it weaker or drop it down to levels that are more desirable to push through these sensitive circuits up here. A lot of these circuits you guys are looking at on the screen here are all things that you have to have specific dB levels coming through, and that's the engineers came up with that, not us at the schoolhouse here. This is beyond even our scope of understanding, truthfully. But this is what they came up with to drop it down by 13 dB, so it gets through this low pass filter here. It goes in this mixer, it gets amped, band pass filtered, all that good stuff. Any questions so far?
No, sir.
Perfect. I'm gonna keep going then. Now we come to this second IF portion, which is 140.4 megahertz, because that's what you're going to get out of this mixer here. That's your second IF. The 240 kilohertz that we had before that first IF is going to be mixed with our injection frequency. That's what this is called. And no, IF is not a shorthand or acronym for injection frequency. Injection frequency has no acronym. It's just going to be injection frequency when we refer to it. Just giving you all a heads up. So the local oscillator 2, to generate that frequency, it has to be, remember that 240 kilohertz that we just had as our first IF? If it's not 240 kilohertz, you're not going to get this 140.4, and you have to have this 140.4 coming through to the next section of the radio. And I'll explain why in a second.
Sir?
Yes.
So what's IF again? I feel like that's going to confuse.
IF is intermediate frequency. Injection frequency is different. That's why I explained that. This is an IF right here, this 140.4 that came through our mixer. You see that?
Yeah,
All
I
right,
see.
that's what's known as the second IF in transmit. The first IF in transmit was what?
The 240.
240. Very good. So we use these things called phase lock looping, and that's how we get our specific signal. And on this diagram here, I can explain that to you guys. This is A3A1. This is what's known as a unsimplified diagram, basically, or the actual block or the actual diagram. This is what's known as a block diagram, just so you guys understand the difference. A block diagram is like the simplified version. This is like what engineers would use if they were coming through and looking to see specifically what's wrong with the components of the radio, if they had to fix something. So what's happening with this thing here, this 140.16, how we're getting that is known as PLL, which is known as phase lock looping, which you guys just saw on the previous slide right here. it takes this signal, this 140.16, which is generated from this VCO, this voltage control oscillator, which generates that specific 140.6, keeps spinning it around here. And all phase lock looping is doing is making sure that it's constantly sending 140.16 to this specific section right here. That's what it does. It locks it in. Make sense?
Yes, sir, that makes sense.
Yeah, it's just, once it's explained, it makes sense. I understand if you guys tried to probably read through this section, it probably didn't make too much sense to y'all. It does make more sense when you get it explained, though. And that's why we call that an inject frequency, if you were wondering why, because it's literally getting injected into the mixer right here. It's not some random name they just came up with because they thought it sounded cool. Hey, sometimes they do things like that. So the 140.4 megahertz, that second IF, is amplified and filtered through this 40 kilohertz bandpass filter. You all understand how a bandpass filter works. I know you all passed EP. It's like going
Yes.
to a concert, correct? If you go to a concert and you have a backstage pass, you can do what?
Get behind the band?
Yeah, you can get behind and talk to the band after this concert's over. If you don't have one, what's going to happen?
You're gonna get kicked out of the whole
You're
concert.
probably going to get kicked out. Yeah, you're probably going to get kicked out. Might be banned for life. Who knows? Depends on how serious they want to be. But that's exactly what a bandpass filter is going to do. It's not going to let anything that's not 140.4 through. And again, this math down here explains why we have that specific frequency. But before we get to that, I got to talk about these digital attenuators here. Yes?
I'm sorry, you said anything over 140 or under?
No, exactly 140. If it's not
anything?
140,
Okay.
it will not get through.
Yes, sir.
Yeah, it's got a little bit of wiggle room, but that's really, the 40 kilohertz bandwidth is just for this 0.4. That's what that's for.
Yes, sir.
Like, that's not really wiggle room. So the digital attenuators that we were talking about next, these are part of what's known as TGC, not THC, the thing legal in Washington State, TGC, transmit gain control. It holds the power at the antenna constant while variable voice levels are coming in. Those variable voice levels, again, if you guys remember, that's kind of the job of the ALC as well. But down here, it's real specific. It doesn't want that fluctuation coming through. And you see that there's a bunch of components in the radio doing that, and there's a reason. We don't want to break any of the sensitive stuff, and I keep reiterating that. So when we mix with our second IF here, that 140.4, which you guys can go ahead and do this math for yourselves if you don't believe me, but I have examples down here, and the variable local oscillator 1, this mixer generates the carrier frequency. Now we have our RF frequency at this point. So we went from IF to RF. RF is what? I mean, it's the main part of our career field. What do we do with the RF energy?
What do we do with it,
Yeah,
sir?
what do you do with RF energy? Where does it go?
Sending.
You send it where?
Sending it.
Out what?
Out the antenna.
Out the antenna. That's the whole point of your career field, to generate
We
RF
transmit
energy.
and receive.
Thank you. We transmit and receive with it. If you don't have that RF, you can't transmit and receive. If this function in your radio is broken, you're probably going to have some issues. Let's just say that much. All right, so let's look at this down here. What is this number? I know I'm asking you guys to reach way back to Monday morning when everybody was just getting up and getting their coffee. We went over this real briefly. What is this frequency?
Frequency range of something.
Yeah, sure is the frequency range of something. That's a real good guess there. I appreciate that. Hey, at least you said something.
Is it the bandwidth of that the radio can?
Okay. Yeah, it's the bandwidth of the radio. I don't like using that word bandwidth because bandwidth, it refers to a number that you're assigned specifically by somebody. For example, remember I was talking about the spectrum managers? You gonna go get coffee, hon? Okay. Yes, please. Oh, sorry guys, real quick. Same thing you're getting. Love you. Hot. All right. Sorry, my wife's getting me coffee. So this is the frequency range for the radio. You were on the right track, Rodriguez, and I appreciate the effort as always. It's the frequency range for the radio. Now, why can you guys see why this 140.4 we have to have it very specific, and why I keep saying things can't fluctuate? Do you see this math right here? You don't have to do the math. Just trust that 142 minus 140.4 equals 1.6, which is this beginning range right here, the beginning number. And then you take the 200.399, subtract it from 140.4 again, and get what?
59.9 bar.
Yeah, which is the top part of our frequency range. Okay, I love you too, hon. Yeah, that's the top part of your frequency range. So remember, that frequency range goes from 1.6 to 59.999. Does anybody know the HF frequency range for the radio?
Is 3 megahertz to 30.
That is the HF frequency range, and we're right. But I said the HF, remember, this is the part I told you guys, pay attention when you're reading. The HF frequency range for the radio. If you know that the starting frequency range for the radio is right here, what can you tell me based on what you just said?
I'm sorry, can you say that again?
So if you know the starting frequency range for the radio is right here, 1.6, what can you tell me based on what you just said?
That's right in the middle of there, obviously.
It's going to be in the middle, yeah, but what is the number I'm looking for? Help him out, Rodriguez. I think you got the answer.
I don't think I got it, sir.
Oh, I think you got it. I got faith.
What was the initial question, sir?
What is the HF frequency range for the radio?
The radio specifically.
The radio specifically.
I know that we were using 2.7
Nope.
yesterday.
That's not it. It's 1.6 to 29.9999 megahertz. That's the HF frequency range for the radio. Y'all got that?
Yes, I hear you.
Okay. Don't feel like dumb or anything like that. You guys are just learning. Don't feel like that. I can hear it in your voice.
Trying to understand.
I know, we're all here to learn, okay? I learn stuff
A
every
lot
day.
of numbers. A lot of numbers.
It's a lot of numbers. Guess what you don't have to do?
Memorize
Math?
the number.
You don't have to do math. Well, eventually at some point you're going to have to do math. But you don't have to do math right now, all right? But you don't have to memorize any of this. It's all in your TO, guys. It's either in your commercial operations manual or it's in your intermediate maintenance manual. Table 1.1 for the commercial operations manual.
Thank you, sir.
Yep, just trying to help you all out. All right, so if we do not have an external PA connected, let me go back real quick, which is that big box you guys saw in the back of the room and that configuration that's typically at command posts, maintenance operation centers, things like that. It will go through this top path here. If we do have an external PA connected, it's not only going to go through this bottom path down here and bypass a bunch of stuff, just like it's saying it's doing, it's going to also reduce that signal again by 23 dB in addition to the 13 that already got reduced. Why do you guys think it's doing that?
I read that it was to protect. Not quite sure. I remember it. I think the equipment itself from
Yeah, it's to protect the equipment
having
itself.
too much out.
Yeah, it's from protecting the equipment itself because you don't want to push too much power through what we're about to go through, which is filters. Filters are very sensitive and they will pop if you send way too much stuff from, and they literally, when I say pop, they literally will just poof into dust. They explode if you send too much stuff. And I have done this before several times in my career. Not on purpose, but it was entertaining when it happened, and then I was like, oh crap, I have to replace that now. Yeah. Because
What are they made out of?
So it had to come out of your pocket?
It's just like filament. No, it didn't come out of my pocket. We had spare ones when I was working on stuff. This was when I was working with speakers at White House Com. I got to go in and actually replace a lot of this stuff, and filters broke all the time. It was just a normal occurrence. We just had to fix it a lot. Mostly because as they're sending the audio signals through various events, things just break. They just break. It happens. But
Gotcha.
yeah, it's fine. Point being, we're going to the A3 next, and that's why it has to be reduced, because we don't want that huge push of power coming through. And with an external PA, we have that power constantly coming through. It's constant. It's not going to like fluctuate. It's going to be constant. That's what I want to get across. It's not like this final PA push here, which is going to fluctuate with the various frequencies of the radio.
Yes, sir.
Yep, no problem. Ask questions if you guys got them. Please do. But the final PA here, again, you note that it says unless it has an external power amp connected, so you're only going to use this when the external PA is not connected. And I say use it, but again, remember all these things are happening simultaneously. Like when you key up the radio, every single thing we just talked about is happening, which is pretty amazing to think about.
That is mind blowing.
Yeah, it is. It really is. And the first time I got taught this, I was like, wow, this is crazy. So the signal is routed through these various filters that we have. Does anybody have the TO pulled up, or should I just ask the question on here? I'm going to take that as a no.
Yeah, I do not.
Okay, I'll take that as a no. That's fine. So I'm going to ask you guys a question based on this table. This is what the table is going to look like, 3-2. It'll look just like this. It's your filter band table. If we had a frequency of 22 megahertz, what band would I be using?
6.
Band 6. Rodriguez, you're all over that. You really don't want to hear right today. I get it. All right.
I'm very competitive, sir.
I can tell. I can tell between the two of you. I like it, though. I like the interaction, guys. I really do.
I'm gonna start yelling. Just get weird.
No, don't start yelling. You're going to blow the
I'm just
speakers on my freaking
kidding.
headset. I'm going to throwing my headset across the room. You're going to hear me yelling. All right. No, that's mostly for the audio recording. If you guys talk too loud, I have to go in there and adjust it afterwards before I submit it to YouTube because it'll clip if it goes too high.
Yes, sir.
That's okay.
Yes, sir. Airman Wright is my rival.
All right, that's all
Is
right.
my rival Rodriguez.
All right, he's your cell or whatever. That's cool. All right, so BCI, that's our broadcast communications interface filter or interconnect filter. I know that's a mouthful. All it's doing is being used for AME mode to reinsert a little bit of that carrier so you can talk to those citizen band radios when you're in AME mode. Again, AME mode is only upper sideband, not lower sideband. The lower sideband mode is called something else. If you want to know what it's called, I'll have to look it up for y'all later. But that's not what it's called. Now, when we have these filters, there's something very specific they want you to note here. Notice how many are being used. What does that say?
2
of
the 9.
2 of the 9. And I can actually go through and trace like we're in kindergarten for y'all and show you that. So we come through. You said we were using band 6, so we're going to come through band 1, go down, go around, doop-a-doop-a-doo. I'm so good at coloring in the lines. All right, go down to band 6, come across. Notice I use 2 filters, go through my high-level limiter, come out, go down, go around, and come out. Everybody saw that?
So the band is a filter, sir?
Yeah, so the band is a filter. On that simplified diagram, you'll see that we only have 1 BCI, 2, and then it goes straight to 8. But there's 8 filters right here, just in the HF alone, and then this BCI counts as a 9th filter. Make sense?
Gotcha. Yes, sir.
Perfect. All right, I'm going to put you guys on a quick 5-minute break while I go use the restroom. I will be right back.
Yes, sir.
I'm back. Everybody here still?
Back and better. Yes, sir.
Yes, sir.
Apologize for that. Can't help real life bios. Alright. So the next thing we're going to talk about in the A3, A2 section here, the subassembly we're in right now, is this VisWAR data stuff. They purposely don't really highlight this high-level limiter thing here for you guys, because what it's doing is literally limiting high levels from coming back into the radio. So as we get this VisWAR data collected, which is voltage standing wave ratio data, as we get that coming back through the radio, which typically is like a ratio, is going to be like 1-to-1 is ideal, 2-to-1 is operable, meaning you can use it. 3-to-1 is like kind of questionable. You generally don't want 3-to-1. That's like the amount of voltage coming back through, because that's going to start breaking stuff. So what this high level limiter is going to do is it's going to stop that ratio, like that, not the ratio, but it's going to stop that voltage from getting into those filters and breaking them, and it's going to shut the whole radio off. That's basically what it's going to do. So the VisWAR data, which is the voltage standing wave ratio data, is produced in this directional coupler here, and it's going to use that tune data to pass on a couple of things. It's going to be used for those TGC circuits we mentioned above in the A3, A1, and then it's also going to be used for this final PA push here to let it know exactly what kind of voltage to push through as the frequencies come through. It'll send that data to those as well, so it doesn't overload those filters. That's what this bias control signal thing is it's talking about. In addition, it's going to pass that information on to the antenna coupler, because the antenna coupler has a really important job where it's going to impedance match, and it does that by passing that data, that control tune data from the coupler, back and forth between its various inductors and capacitor elements, which I can show you right here. Here it is. You guys see the inductors and capacitors?
Yep.
Perfect. So here's capacitors, there's inductors, there's some more inductors down here. And it's going to pass those back and forth until it gets the right number, or the right impedance match, basically, the right voltage match resistance, because that's what impedance is. It's our resistance, yes?
Yes, sir.
Perfect.
Yes, sir.
And then it sends that information out to the antenna once it gets it.
Sir?
Yep.
Could you explain the bias control one more time, please?
Yeah, so bias
Is that like
control, bias control is the information that's passed from the directional coupler, this VisWAR data, this voltage standing wave ratio data. It passes it to the final PA, the final power amplification, because it needs to know how much power to push through, how much final amplification really to push through based on your frequency and how much the voltage standing wave ratio actually is, so that when it goes through these filters here, it doesn't break them. Yeah, filters
it's
are
not
very
sending
sensitive.
the actual data that's coming through, it's sending a different signal,
No,
letting
it's the
know how
data that's
much.
coming through. So like there's initial data getting sent through, and then when it happens, it immediately sends that data back and readjusts.
Oh, okay.
So
Yes,
it does let that through. I get what you're saying. So if like something is busted ahead of time, yeah, you're probably still gonna break something if that's what you're trying to ask me.
that's what I was wondering. I
Yeah,
was gonna
that's
say, if it's
entirely
already going through
possible. That's
initially, then
entirely possible that if something went through initially, you could end up breaking it.
yes, sir.
Yeah, that's entirely possible. That's a great question. I don't think anyone has ever asked me that question. I
Thank
like
you, sir.
that. No, that was a great question. You guys are full of good questions today. All right, so this is just reiterating what the A3, A5 does. I've just told you, but I'll read it for you anyway. Impedance matching is done in the antenna coupler, which takes place between the radio and the antenna. It's fed to the J7 antenna connector, which is 50 ohms. It compensates by switching capacitors and inductors. The J7 antenna is going to be an antenna of your choosing, which is what it's saying on the bottom there. You guys will choose based on the mission type you're using. So for example, we would use like a NIVIS or something if we were trying to go over a mountain. That's what NIVISes are typically used for. They're near vertical incident skywave antennas. That's all that refers to. The OE505, the antenna that's included with the radio, is used a lot because it does the full frequency range of the radio. That's why it's included with the radio. There's really simply no other reason. So my first question for all y'all is, what is TGC? What does it refer to?
Rodriguez, you gotta take this one.
I pass it to Sotelo.
Oh yeah, we're just passing around. All right, so tell me about it. He's gonna be like, that's stuff that's not legal in Washington.
I remember the context, but I can't remember the exact definition.
So it's called transmit gain control. I'll give you that much. I'll let you struggle for another couple seconds here, and then I'll give you the answer. Man, if only there were 2 more airmen in class who could help us out.
Pass.
Pass? Thanks.
Nadolski.
Nadolski. First thing I hear you say is pass. Alright, so I'll say it one more time for y'all, and we'll go back to the section where it's at.
Wasn't it how, like, it converts
I got you.
power?
I got you.
It's too late now.
TGC is part of the transmit gain control. It holds the power at the variable voice levels constant as they're coming in. It holds the power constant at the antenna. So you guys see this right here?
Yes, sir.
Remember this because we're going to have something similar on the receive side, but we're going to change the name and it's going to change its job a little bit. All right, let's go to the next question. Why is voice converted to digital data? Everybody should know this one.
When it's in digital data form, it's easier to modulate than analog.
Yep, it's easier to modulate than analog. Very good. Where is the second IF located? Nadolski.
I have no idea.
You have no idea. Okay.
I have an idea. I'm not sure how exactly you want us to answer the question.
However you want.
But I have. So when it gets to that point, there's the first one that puts in the 240.
Yep.
kilohertz,
So the first IF is 240.
The second IF puts in the 140.19.
Nope. You were so close.
140 point. I think it's just 140.1.
Nope.
Or is it 140.9?
Nope.
It's 140 point.
Oh man, this is gonna be awful to listen to on the recording. Okay, you're struggling. I'm gonna help you.
I'm struggling.
It's okay. So here's our second IF. It's 140.4 megahertz, and it's located in the A3A1 subassembly or the A3 assembly.
Yes, sir.
Everybody got that now?
Yes, sir.
It's okay. I could tell you were struggling for a second there. I'm not going to have you do the entire transmit path. If you guys want to do that question, you can come back through and watch this video again. That's entirely fine. We don't need to review that again. We just did it. Where does digital modulation take place, though? That I want to know.
You're talking about which A2 or which A it comes from?
You tell me.
A1 assembly?
There's no A1 assembly. That's the chassis.
Chassis?
A3, A4.
The first IF.
Oh, now we're just guessing.
What?
All right. A2A1 is where digital modulation takes place, specifically in the subassembly A2A1, and specifically even further in the component, the digital intermediate frequency application specific integrated circuit. It's like an onomatopoeia right there. Super long. Any questions on clear voice transmit, guys? The rest of these slides are going to go fairly quick from this point on because as long as you have a general grasp and understanding on how transmit works, receive should be very simple for you. This is where that digital modulation takes place, by the way, what I was talking about. So that last question.
A1, sir. A2A1, sir.
That is A2A1. Don't worry, you're going to get asked these questions again tomorrow during the review.
Positions?
Could I name them? I could,
like
but I would much prefer if you did it.
Well, I know that's A2A1. The first one should be A2, A3, A2A4. A3A4?
A2A4.
A2A4.
A3 is responsible only for doing analog RF sections of the radio, so it's not going to be digital modulation, things like that, and voice cleanup.
Yeah.
Remember when we talked about difference between assemblies and sub-assemblies? That was one of the things I talked about. That's okay. It's okay to get things wrong. I'd rather you just keep taking guesses. That's totally fine. All right, if there's no more questions on clear voice transmit, I'm going to do our interim summary, and then we're going to continue. So A1 to A2, A4 is the analog to digitized audio. From this point, that's what we're doing in this whole section here. A to A1, again, responsible for digital modulation and that digital to analog conversion, because we can't take digital format into our analog section. It doesn't want it. It's not going to process it through that stuff. A3A1 is going to be your IF to final RF. That's your KDU frequency, the number you guys actually program into the front of the radio, that frequency y'all were doing in lab, or the one you're going to do today in the PMI lab. And the A3A2, that's our final push, our final power amplification push, but we don't use that if what's connected?
The base, the
starts with external, ends with PA. External PA.
That's it. That's just
That's
the
it.
external
That's
PA.
it. The external PA. Very good, Amrite.
I thought there was
That's
something else in between there.
No, that was it. All right.
You said it's usually only equipped when you're at a base station.
Yeah, base station configuration or command post or MOC, which is your maintenance operations center. Those are like the big airfield people. They're responsible for like managing the airfield.
Yes, sir.
So then we go to the post selector filtering because it happens at the end. That's what that network was called at the end there. I know I didn't note that, but it's called the post selector network because it happens at the very end of the radio. We're going to have a different name on receive. You guys should probably be pretty easily guessing that right now. VISWAR is your voltage standing wave ratio data. That's, again, very important. That allows us to do that bias control and also make sure that the correct data is passed on to the antenna coupler, the A3, A5, which is then going to do that impedance matching based on that using inductors and capacitors. Any questions so far?
No, sir.
I know this is a lot of material, guys, and that's probably why y'all aren't talking very much. You're probably just in note-taking mode, I assume. But please ask questions because I can't help you if you don't help yourselves. Right? I understand this to the level I understand it, but I can't understand it to the level you understand it if you don't help me.
Heard. Thank you, sir.
Yeah, no, that's fine. I'm here to help you guys. I know this stuff is confusing, trust me. All right. So,
I'm more of a visual learner, sir, so I have to look at it a few more times before I
yeah, and
understand.
that's fine. That's fine. That's why I do these videos for you guys. That's totally understandable. The video hopefully does help you all.
Much
To me, I'm
better.
more hands-on. I can understand the concept, but I don't.
Yeah, so when you go through and you're doing the PMI today, make sure you pay attention to that. And that'll think about this stuff that we're talking about right now as you're doing the PMI. And that'll help you kind of remember it. So that's great too. So next we go to the J3 data. We're going to talk about data next. If you'll notice, there's a lot less red lines because once we get to this point here, everything's going to be the exact same as it was with audio. But first we'll explain what's happening here. The J3 data is what's known as digital because we don't talk in ones and zeros unless some of you do. I don't know. Maybe Nadelsky. He doesn't talk very often. He might be a robot. I'm not sure. So J3 comes in as data, goes to DTE, that's the data terminal equipment side. That's just going to be where it hooks into, that's all it is. Then we go to the PTF PGA, that's the plain text field programmable gate array, or as I called it, the what?
That's the Boston Copper.
The Boston Copper? Yeah, that's the traffic cop.
Traffic
yeah,
cop.
That's a traffic cop. All right. I didn't know he was a cop. All right. So here we go to PTF PGA. And plain text data, it's going to go to the bottom. It'll go to CFPGA next. That's your control field programmable gate array. From there, it is data this time. So it goes to the modem. All data has to be processed through the modem, and all encryption types have to be processed through the modem as well, whether they're on analog or data. And I'll say that again in a second when we go through the encryption portion. Just remember that. From here, from the modem, it gets modulated and then goes to the CDSP. And then there's nothing different at this point. It does exactly the same things that our analog signal did. Any questions on data?
No, sir.
Pretty
Yes,
easy,
sir.
huh? You guys see what I meant? Like it's going to go quicker now?
Yes, sir.
Yes, sir.
Perfect. If you would like to follow along in your TOs, or if you need to look this section up later, it's paragraph 3.2.2/3.3.2.4, and this is in your intermediate maintenance manual. That's transmit clear voice signal flow for encryption for CC and CT. And then there's transmit clear data signal flow below for CC and CT, and that's paragraph 3.3.1.6 and 3.3.2.4. And that probably gives it a little more breakdown and explanation than what I'm giving y'all right now. I'm just kind of giving you guys the summary from the stuff I know. So J1, if it was audio encrypted, it's going to come in as analog. Go to our ALC. What does our ALC do, Airman Wright?
ALC is the adjusting level.
Mm-hmm. That's not what it stands for, but
Cs.
you've got the right idea. That's what it's doing. That's not what ALC
Yes, sir.
stands for. Yeah, ALC
I'm not sure
stands
exactly
for
what it stands
automatic
for, but I
level
know it
control.
adjusts automatic level control, but it does adjust the level of the volume that you're
Yep,
putting it into. So
absolutely it does. Very good. Very good. And then it goes to the AIC. What does the AIC do, Rodriguez?
Is the
Got him.
AIC like is it a filter?
Nope. I'll zoom in and enhance.
Digitized audio, so is it converting it?
Yes, it is. Very good.
Okay.
I enhanced that for you. I think it helped. From there, we go to the VDP. Airman Smith, I haven't heard from you in a while. What does the VDP do? Smith? Bueller? Crickets. All right, anybody. I'll pass it up to anybody. What is VDP doing?
Satella, you want one?
Huh?
I said to Satella, do you want one?
Somebody.
Don't be nominating me for stuff.
I was just
All right, Satella, what is it?
That's a good question. I can't remember.
All right. It enhances and cleans up that audio. That's what the voice data processor does. And if you guys think about these names logically and I spell them out for you, it makes sense if you think about it, right? Automatic level control, adjust levels. Analog interface chip, takes it from analog to digital. Voice data processor, all it's going to do is clean it up, just like a data processor would.
yes, sir, that
PTF
actually does
PGA,
help.
yeah, it does if you think about the names. And they're all spelled out verbatim in your TO. So there should be no question on what they're doing. And there's also a glossary. The PTF PGA, that's your plain text field programmable gate array. That's the traffic co-op. So if it's audio or data, it's going to come in and go up. If it's CT, it'll come out of our A2A4 subassembly and go into its own separate A2A5 subassembly, which will be used for CT encryption only. That's the one we don't share. And then if it's CC mode, it's going to come through and go to Citadel cover mode, go through its little encryption chip here inside of the A2A4. Then it's going to go to CTFPGA, like both of them will travel. And that's the ciphertext field programmable gate array. That's our super traffic cop there. And then it becomes black at this point, which is known as encrypted data for radio purposes. This I want to touch on real quick because when you get to your units, you may hear this differently. Red may be black, black may be red. Just pay attention to whatever the local ComSec guidance is without getting too much into that. But for our purposes, black means encrypted.
Sir,
Yep, go ahead.
I got a question about the
Sure.
difference in what it's doing for the CT and the CC. If they're both encrypting, what is?
So
Like,
CC,
I know the CC is the one you could share.
yep. So
with
great
people.
question. Great question. So CC is Citadel cover, right? So that's the one we share. It stays inside of this section because it gets programmed from the KDU or from a remote application or something like that. It does not need external encryption. External encryption is only loaded into that A2A5 embedded crypto assembly. That's why they're separate. That
So
J18, the fill
is that
port,
just like extra encryption that is put on there for when you're sending it?
I don't want to say it's extra
Not on
encryption.
base?
I just want to say that it's NSA certified encryption that's coming through there.
Yes, sir.
They're different types of encryption. Does that make
Sure.
sense?
But those are
So for that, it's just like another wall of security, kind of.
Exactly. It's like having a firewall or a border guard or something like that, if you guys are familiar with those things.
Right, and then so the red interface, does that mean that it's not encrypted, or
If
does
it
that
says
mean
it's
that?
red, it means it's unencrypted. So if you're absolutely 100% like working with other agencies and stuff, make sure you pay attention because red on their side may mean encrypted. like a SIPRNet cable, is red. So you might get confused. It's entirely
Ah, okay.
possible. That's okay. You guys are asking great questions. So the BIOP is next. Since we're sending that encrypted data through, it has to go through the BIOP. That's the black input-output processor. That's what that stands for. It maintains system status and control functions for the radio, as well as it processes this encrypted information into the modem. Notice I said information because it could be data or audio. Both things get processed on the encrypted side through the modem. I'll say that again. Both audio and data get processed through the modem on the encrypted side. And then they come out the CDSP. That's the control data signal processor. And then they go same throughout the rest of the radio. That's it. Nothing's different, guys.
So they're processed before and after going to the modem?
Absolutely. Yep. Absolutely. Yes. Questions? Pretty easy
No,
so far?
I have a question.
Oh, go
Could you
ahead.
say that again?
Could I say what again?
Your last sentence.
My last sentence.
The process before and
Oh, okay. I was like, I could say my last sentence again. Absolutely. All right. Black is the encrypted portion here. And then it goes through the BIOP, which is the black input-output processor. From the BIOP, this is responsible for maintaining system status and control functions for the radio, as well as if it's audio or data, it will go through the modem because it's encrypted. That's why. It has to pass that encrypted information through the modem. From there, it comes out and goes to the CDSP. Is that what you meant, Sotelo?
that was Nadal.
Oh my gosh. Sorry, Nadalski, is that what you meant?
You were talking about it's past, like, I was confused because you said it's passes like both audio and data.
Yeah, your intelligence. Data comes in J3, that's digital. Audio comes in J1, that's analog.
Okay.
That's what I meant.
Okay.
No, good. I'm glad I could clarify that for you. Next, we're going to go to the
Do
receive
you say
section.
data is always digital?
Data is always
digital?
digital. Absolutely, 100%.
Oh, okay.
All the time.
Thank you, sir.
No problem. Paragraph 3.3.1.2 in your intermediate maintenance manual, we're going to talk about the receive clear voice signal flow. I'll give you guys a little Where's Waldo search here real quick. Tell me the 3 things that are different with this before I move on. This is receive.
There's more functions that go on before the filtering.
Okay. That's not one of them. That is different, but that's not one of them.
I didn't notice the directional coupler on the last one.
You didn't?
I noticed it now.
There you go. I'm here for you.
I noticed it now.
Okay. I gave you guys 2 cracks at it, and that's good enough. So the top and bottom modules are swapped. That's the most obvious one. The handset and the antenna are swapped. Duh. And then each module's components are reversed. Plus, there's a notch filter. This guy right here. Thing that looks like a seagull that you draw in kindergarten.
Yeah. Upside down duck.
That's exactly what they look like. Yep. All right. So, like I said before, job functions don't change for components as they come back through. We just added a couple things in the receive side. The antenna coupler, again, going to do that impedance matching for that VISWAR that it did with those inductors and capacitors, just like it did in transmit. Directional coupler, going to do the same thing, pass that VISWAR data along. That's all it's doing. High level limiter, same job, just checking for that ratio to make sure everything's good to go before it gets through our filters. And then we're going to go to the pre-selector filter network, which is going to use how many out of 9 filters?
2.
2 of 9. So you guys got that one. At least I know you're paying attention. So you got 2 out of 9 filters. Very good. From there, we go to something called the notch filter, which is new. It's going to act just like our final PA did. However, it is not an amplifier. Similar, but not an amplifier. It's going to take that signal that's weak because it's got filtered, it's gotten sent across the ionosphere. We don't know how far the person was we were talking to from us. I mean, typically you will know, but who knows? They could be moving around. It's got all this other stuff that's happening, filtering, things like that. Yes.
So for that, when we on the transmitting side, there's the bias control. So for the receiving end, is that not a thing because it already goes to the high level? Or is the bias control
the bias
still?
control is still there. It's just not being used in receive.
Yes, sir.
We don't use that in receive because remember, I'm telling you, it's not an amplifier. That's why.
Yes, sir.
The notch filter has a simple job. It just does exactly what it says it does. It's going to boost that weak signal and put it up to 140 megahertz. That's what it's going to do. Because we need it to be at that for this next part. When it comes to our analog RF section, our A3, like we talked about before. Now, one big major difference here is our first IF in receive is what, if you notice from these notes?
The first IF is 140.4.
Right. So the first IF in receive is 140.4, whereas the first IF in transmit was what?
200.
You get, come on. Where's the rest of the number?
200.3. I don't want to make a dumb
Is
guess.
it 200.2? I thought it was.
It's 240 kilohertz. Good job, guys.
240.
240 kilohertz.
240?
240 kilohertz is the first IF.
I thought it was 200.
It's also right over here, if you forgot. So 240 kilohertz is the first IF in transmit. In receive, it's going to be our second IF, 240 kilohertz. And that's really the biggest difference here, besides this AGC thing. And that's the only things that are really different in the A3 section here. You've got AGC, which is automatic gain control, which is still going to do the same thing. It's going to adjust those varying voice levels and keep them constant, but it's going to do it for your receiver, your handset instead. Makes sense? Nothing else really changed here. We then mix it again with our local oscillator 2, except now we're kind of, think of it like it's extracting it out. So we're subtracting it rather than adding it. We're subtracting 140.4 from 140.16 and getting 240 kilohertz. So everything's getting subtracted on this side. Making sense so far?
Yes, sir.
Perfect. Pretty easy. Honestly, if you guys have a great grasp on how it comes through on transmit, this really should be super simple for you. From there, we go to A2, A1, which is going to do digital demodulation now. So the signal enters the A/D converter before being demodulated at DIF ASIC, the digital intermediate frequency application specific integrated circuit, which the output will be intelligence. So the signal is then converted to analog audio signal. It finally is sent to the J1 audio connector, where it is sent out. So the signal is then converted to the analog audio signal, which is finally converted and sent to the J1 audio connector, just like you guys were doing in class. Now, what do you notice is not here on this side? What are we missing?
The ALC.
The ALC, outstanding. Why are we missing the ALC? What can you do? What can you do with your fingers if you can't understand somebody?
You change the volume on
You
the
guys
radio
can change
itself.
the volume on the radio itself. You don't need somebody to automatically adjust the levels because you can do it yourself if you can't understand something. Make sense?
Yes, sir.
Pretty easy, the receive side, guys.
Yes, yes, sir.
All right, so this is blank for a reason, and I encourage you to fill this out yourselves when you come back through and listen to this again. That's why this is blank. Typically, if I'm in class, I'll go over this part with you and have you guys fill it out, but I encourage you when you listen to this again in this recording to do that again, okay? Any questions on clear voice receive?
No, sir.
Did anybody notice this was a transmit diagram?
Yes, because the J1 and the J3 are on the wrong.
Yep. Pretty funny. All right, so our data path, everything is the same coming back through on the data path. And then it goes from CFPGA to PTFPGA, the traffic co-op, right? The plain text field programmable gate array. And then it goes to the DTE, the data terminal equipment interface. And then out through the data port right here, the J3 data port. For encryption, the real big change here is it goes to the CDSP, the control data signal processor, into the modem because it's encrypted. You guys know it has to be demodulated now because it's coming through on that side. Goes to the BIOP, the black input output processor. From there that maintains and control and system status functions for the radio, just like it did before. Passes along that black encrypted information because it is still black at this point. It is not red. Red is unencrypted. From there, it goes to the CTF-PGA, the ciphertext field programmable gate array. And then it goes to the A2, A5 crypto assembly, the embedded crypto assembly. If it was CT mode, comes out as red, unencrypted, so that you can understand it in your handset, or you can understand it as data. From the CTF-PGA, it'll go through, do the same thing. If it's CC, it comes out and stays in A2, A4. Any questions, guys? That's really all we had to go over.
Yes, sir. I have a question.
Okay, go ahead.
So the unencrypted coming through does not have to go through the modulator on the receiving end?
No, it does not go through the demodulator on the receiving
Or the
end,
demodulator,
unless it's what? Unless it's what?
Unless it's...
See what I highlighted?
I can't.
Data? Unless it's
Oh,
data.
unless it's data.
Yeah, so if it's data, it has to go through. Remember that, guys. It has to go through if it's data. But yeah, very good question.
J1. Thank you.
Anything else? Ask your questions now, guys. We're going to go over this again tomorrow for a review. Not the whole thing, but we're going to review. I have a couple questions to ask y'all for tomorrow. I expect you all to have your entire appraisals done tomorrow as well.
Where will we be turning those into, sir?
You don't turn them in. You
Pictures
guys
of them
don't turn them
or...
in. Don't worry about any of that.
We're
Hold
just
on.
gonna go over
Hold on.